have designed a lug clevis. Okay, and now your question is, how do I attach it? This is something we talked about in class. You know, it's like you want to try to load it in shear.
Okay.
So where would you go?
That's what we know the direction of where the hole for the lugs are gonna be and all that.
Okay.
And we're like maybe 80% sure that we just want to use one side. Just
okay, so you want to use one side. So in this case, which side would you use? This side or this side?
We would use the bottom side.
Okay, so then you would bring it down like this. Okay, and now you're going to bolt it on, and you're going to have to figure out how many bolts you want. Okay, so now basically is okay, I'm now going to have to figure out how thick of a flange I want to make. Right?
Okay.
And then, you know, this is already going to be, you're going to have kind of this set up, so now you got to figure out how I want to transition from all of here down to here. Do I want to, you know, taper it down a little? Do I want to radius it? You know, you get to do something like that. And so now I'm going to come over here then and eyeball it this way. So now here's my hole, here's my lug, and now I'm going to, here's my part, right? Here's the structure I'm trying to attach it to. So I know that, for example, let's say I have a force like this and a force like that, and now what I would do in this case is, you know, set up something like an Excel spreadsheet where I am now going to play with some variables. I am going to say, okay, I'm going to say, how many bolts am I going to put in here? Okay, so set n equal to some number. In this case, it would be 9.
Okay.
Then I know that the bolts are going to have a diameter d. So d is equal to something. Pick a number.
Okay.
All right, and then for the thickness, I'm going to pick that. So set a cell up for that. This is known, right? This px is already known, and this py is already known. You've already figured that out.
Okay.
And then you're going to correct those by a fitting factor. So I've already told you to multiply those by a fitting factor. So you're going to multiply your load by that fitting factor.
Okay.
So that's already given. Okay. So now you basically figure out, okay, I'm going to use 9 bolts. So then I'm going to say, okay, and then you start doing some things like, okay, P bolt X, P bolt Y is basically what, you know, Px divided by N, Py divided by N. You know, you now start doing those kinds of things.
Okay.
And now if I change N, I change that, but I only have to change it over here, and it's going to take care of it down here for me in Excel.
Okay.
The next thing I may want to look at is, what is my bearing area? My bearing area is going to be the diameter d times the thickness again. So now your Excel sheet is going to calculate that for you. And if you change t, it's going to change the bearing. And then I can calculate, for example, then I could do something similar to this to start looking at, you know, where I take this and I put, you know, the moment in the centroid, and then I calculate, you know, that other stuff.
Okay.
But then I could start doing that and building my table, my spreadsheet, and now I can go back and start playing with this guy here and this guy here and this guy here to get to the point where, because what you do is you just keep moving down so that you calculate, for example, the bearing stress, which is going to be the load divided by the bearing area.
Okay.
So you start moving down, and then you calculate your design factor, which is going to be your yield divided by, for example, the sigma bearing. So you would pick a material, or you could go and say, well, I want to try to figure out what the best material would be, so what I'm going to do instead of this is maybe say, okay, I'm going to start looking for a material that satisfies this.
Okay.
And then I had got to get this or better. So if I'm slightly better than that, then I would go back and calculate what. So you can see how you start doing this.
Okay.
And now,
Where does I saw something that it was like eccentric load for each individual.
well,
hole?
yeah, what's going to happen is you're going to have an eccentric load where, for example, I look at this. So each one of these is carrying a small contribution in this direction, right?
Okay.
And then they're also carrying a small contribution like that. Right?
Okay.
But then, this force is also, this px is also trying to twist it. So there's also a portion that's trying to resist the twisting. So this is trying to twist it like that. So this one's going to have a force doing like that. This one's going to have a force trying to resist it like that. This one is going to have a force trying to resist it like that. This one's going to have a force trying to resist it like that, like that, like that, like that, and like that. You see how that works?
Mm-hmm.
So that's what we call there's a concentric portion and an eccentric portion. So these portions are the eccentric, and then the concentric ones are just the ones that are just like this.
Okay. Okay.
So that's what's going on there. And so you kind of have to take that into account. But you can see how you can start building this to do that.
Okay. Okay.
And then you would repeat the process with the other two fittings. But you can see that by building like an Excel sheet or something, now I can look at the variables that I have for the design, which is the number of fasteners, the diameter of the fasteners, the thickness of this material.
Okay.
And then of course I'll also have to look at the spacing here, the spacing here, you know, for example. And again, you can also have that.
You put that also into
You would
Excel?
put that into your spreadsheet. You would put the things that you can adjust. You as a designer have control over what this looks like.
Okay.
And so you would put those things in there, and then you could just adjust and play with them as you go along. These, like I said, are going to be fixed. You've already done your load calculation, so you know what these are.
Okay.
You have control over the material that you're selecting. You have control over the geometry.
Okay. Is that going to be kind of the same idea using an Excel sheet when you're shaping the actual like hinge part of the lugs?
Mhm.
Okay.
If we look at the lug portion, let's look at that. You again have this diameter, you have the lug radius, R, and you have the width of the lug, W,
Okay.
right? And up here, you also have how thick the lug is.
Okay.
So-
Also the angle, like you talked about the angle of.
The lug axis, and then your load axis.
Okay.
Okay, so let's just do a generic lug here. So that one goes up like that. So this, what I'll call theta axis. That's the axis that this is the lug axis.
Okay.
Okay, this is still your diameter D. This is the radius R. This say is your lug thickness, the lug width. Okay.
Okay.
Now I have forces that act on this. So say I have a force here and a force here. The resultant looks like that. So this then becomes theta load. What I call theta load.
Okay.
And then the design curves are based off the lug axis. So it's the angle that the resultant vector makes with that lug axis. So I'll call this theta applied, just to differentiate the three. So there's three angles that I'm considering. One is geometry, the lug axis itself. That's based on how you design your lug. The load angle is based on how the loading works out, whether it's more up like that and it's tilted more like that or tilted more like that.
Okay.
And then the other one is going to be the difference between, it's going to be a combination of the geometry and the loading.
Okay.
So you are going to then calculate a couple of things. You're going to calculate your R over D, and the W over D. Again, these are what you have control over.
Okay.
You'll go to that design curve that we had, and you're going to find your material, which is SU, the yield strength of the material. You're going to find a ratio on the design curve, which is called SBR over SU. On the curve, it's actually written as FBR over FTU. They're the same thing, right?
Okay.
And then there's also going to be the lug correction, theta over that. And then this, when you do that, is going to give you the lug bearing allowable. And then sigma bearing for the lug is going to be P, the resultant, divided by the bearing area. And then your allowable, your design factor is just going to be, and this is all for the lug. And there's an example posted on Blackboard that walks through all that.
Okay. Okay.
Any questions on any of this?
I mean, I guess I'm not too good with Excel, but I think people in my group will be able to. You just like incorporate the formulas into Excel.
Yeah,
Okay.
you would essentially. There's going to be cells that are be for variables that you change the numbers in,
Okay.
and then there will be cells that will you nest a calculation in,
Okay.
and those cells will then read values.
Okay. So it's kind of like MATLAB programming,
Exactly.
kind of. All right.
It's going to work just like that, and it's going to have. It'll be, for example, just to give you a quick rundown, and what it would look like is. It's going to be an array, so there's going to be rows, and so it'll be, I think, A, B, C, 1, 2, 3. I'm trying to remember how they orient it, but in other words, this is going to be a cell, and you'll be able to put a number in there. So you say put 5, and let's say in this one you put 3, and then this one you will then say equals whatever is in this cell, so let's call that A1 times whatever is in A2. And then that's going to give you, when I look at it, it's just going to say 15. And now if I change 5 to, if I get rid of that and say 6, it's then going to update that to 18.
Okay.
And then you can, so when you put an equals in there, you're basically telling Excel that I want you to calculate something. And then if I just put a number in there, I'm telling you this is a variable.
Okay.
So that's how it works.
All right.
Any other questions?
No, I think that's
Okay.
perfect. All right, sweet.
See you Monday.
Sweet.